All right, so now let's talk about the equipment you're going to be using. These are standard breadboards that we'll be using all semester, and the way they're wired is you do not have to twist wires together or solder them together. All you've got to do is poke the leads into these little holes, and they will be connected for you. And the way the breadboard is organized is shown underneath here. We have these metal bars running vertically in the field and running horizontally at the top and the bottom. The vertical bars here means that all these 5 pins are all interconnected. They're all shorted together by one of these bars. One warning about these, please do not try to poke thick wires into these holes. You'll just bend the prongs, and then later on they'll be bent and thin wires won't be grabbed anymore. So try to use thinner gauge wire like you're going to find on the components we use in here. So this area is the field, and they're all vertically connected. You have up to 5 connections. And if you need more, you can always jumper next door and put more of them there. And then the fields that run across the top and across the bottom are for power supply that are common to the entire structure. So any power supply you plug in on the end here is going to be valid all the way to the other end. And this has 4 power buses on it. So if you're running op amps, for example, you can have plus 15, minus 15, and then use these others for ground. So you can run up to 4 different power supplies to your circuit. These boards are nice. I'm hoping that you all have your own. If you don't, you can come in and rent them from Steve for a very moderate price. I don't think he lends them out for free. So try to get one by the time you come in for lab. Okay, so this is the breadboard we're going to be using, okay? And it's got binding posts on here to connect up to the power supply, and then everything else is going to be connected through alligator clips. Next thing we have is our DC power supply. This one has 2 outputs, red and black. Red and black are the 2 outputs, and they float. And the advantage of doing that is if you want to make a positive voltage, you tie the negative to ground and the red is a positive. If you want to make a negative voltage, you can tie the red to the green and use the black as your negative voltage. So this power supply can do plus or minus voltages. For this lab, we're only doing a single positive voltage, so we're going to only be using the left side here, the first one, and we're going to jump negative to ground so that if the negative is a 0, this has got to be a positive voltage. One precaution I recommend is that you always turn your voltage down before you turn these things on, so turn the knob all the way down. The previous unit might have left this maxed out, and if you connect it up to your circuit, and it's more voltage than your circuit was expecting, you could damage your circuit. So please turn these knobs all the way to the left before you plug anything in. And sure enough, the voltage is 0 and the amperage is 0. And then this is the meter for the power supply on the left. This sets the meter for the power supply on the right. These are both zeroed out. So make a note of this. This is a Keysight EE310A, number 741. In your lab report, you'll be asked to make a recording of all the equipment you used, including make, model, and catalog number. That way, if we have defective equipment, we can trace it down. It's a good habit to get into for the rest of your life as well. Over here, we have our 2 multimeters. These can measure current or voltage or all this other stuff, DC volts, AC volts, DC current, AC current, resistance, frequency, as well as temperature if you get a separate temperature probe. And so these are actually quite versatile. These are also very good quality. You can tell they have a lot of digits on them. A lot of meters are only 3.5 or 4.5 digits. These are way more than that. You'll also notice the numbers dancing around, and that's because they're picking up noise in the air. This is plus or minus 100 millivolts of noise coming down in the air. It usually comes down from the 60 hertz grid. Once we connect it to our circuit, that will settle down. So let's designate current and voltage, I and V, and so we can go ahead and wire our circuit.
What were the numbers?
Okay, yes, these are both Keithley model, don't tell me, 2000 multimeters, both of them. The top one is catalog number 366. The bottom one is number 364. Okay, very nice meters. Please treat them with respect. Okay, so the first thing we're going to do is we're going to turn the voltage all the way down, and we're going to start to wire our circuit. And we're going to use, which was the 4148, was the medium-sized glass one?
The smaller.
The smaller, this one. Okay, so this is the diode that we're going to use. We have our resistor already here. This is a 1K resistor that's specified here. I chose a value of 1K because we don't want to go above plus or minus 12 volts and plus or minus 10 milliamps. So 12 volts over 10 milliamps is about 1K. Also, 1K resistor is a very common value. The color code is brown, black, red, gold. Don't worry about memorizing. You will have memorized it by the end of the semester. Okay? So let's start with our connections. We're going to come from our DC supply through the resistor, through the ammeter to the diode. Now, we could go from the supply to the resistor, back to the ammeter, back to the board, but it's simpler if you go from here through the ammeter and then to the board. It'll save you some wiring. So I'm going to do that. I'm going to use our red lead here that goes from the positive output here to the current input, which is the white terminal on this, and set this for DC current. Okay? And then we're going to connect the negative of our power supply to the ground terminal on the board over here. These binding posts are very nice. It's a good idea to tuck in the wires whenever you can just to keep them out of your way, and if you ever have to troubleshoot, or I have to troubleshoot. And then coming out of the ammeter, we're going to now come to the board. So coming out of the ammeter, the output for the ammeter is this black terminal here. We're going to go to the plus side of the board, and the plus side is already wired through this purple wire to the upper bus. So we're going to connect now the resistor to the upper bus on one side and then down into the field on the other side, and it can be anywhere in the field. Okay? And then we're going to connect our diode with the stripe down initially. We're going to check forward bias first. We're going to go from there. Actually, let's spread this out a little further so we don't need any jumpers. From there, the ground bus is this lowermost bus down here to there. And try to get it to go in the hole. Some of these holes are bent and the wires don't go in very easily, like this. So we now have the diode coming from the ammeter through the resistor to ground. And then the circuit is basically all connected, and all we have to do now is connect up the voltmeter. So to connect up the voltmeter, we have to connect the negative side here to ground. And it doesn't matter if we connect it to ground here or ground there. It's much more convenient to there, or even, no, we don't want to do that. Or we could even run it back to here if you want to keep it out of the way. Ground anywhere is ground everywhere. And then the positive side of the voltmeter that's left is the green wire, is going to be this. We're going to put the voltmeter on DC volts, like so. And we're going to connect this to the diode itself. So for that, we need an alligator clip. These alligator clips just plug onto the end of the banana plug, and we're going to plug it in there. And you'll see that everything has quieted down. We're now reading 11.5 millivolts, which is basically zero. There's probably just a little bit of residual coming out of here. We're reading 0.00012 milliamps, or we're reading 0.12 microamps of current, which is basically a sneeze. It's very, very little current. And our circuit is already built. Okay. So what we're going to do now is we're going to build up our voltage, gradually raise our voltage, and we're going to measure current and voltage using these two things. So what I'm going to do is in forward bias, let's do 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.8. Let's go in 1/10 volt increments until we get to our maximum of 10 milliamps. Okay? So what I'll do is when we get to each point, I'll stop. It'll be incumbent on you to record your diode current, your ID, and your VD in a table. And you'll have to give the table and graph it as part of your lab report. Okay, so we can now gradually start to turn V1 up, and we're going to stop when this reads 0.1 volts. Might want to stop here and take the measurements as your origin. So at 0, we've got about 12 millivolts, 0.012 volts, which is basically 0. And we've got 0 current. So now let's bring this up to the point where it stops at about 100 millivolts. Right there. So at 0.1 volts, you can measure this data point, 0.1 volts. And again, we have 0.15 microamps of current. basically 0. This won't even show up on a graph. So let's go on to point 2. It's a little bit touchy. So at 0.2 volts forward bias, we're still at, what's that, 0.28 microamps. So again, virtually no current. We're going to stop at 0.3. Okay, it's kind of touchy. Again, we're starting to creep up a little bit. We're now at 1.4 microamps of current. Again, that will not show up on a graph. So we're going to get to 0.4. And we're starting to creep up a little bit on the current. We're now at around 1 microamp of current. You can see how sensitive these meters are. Okay, so let's go to 0.5. And we're now, the current's coming up even further. We're now at 69 microamps. At 0.6. We are now at 575 microamps, or 0.575 milliamps. So now this diode is coming alive. We're coming into that upward bend. And we might not even make it to 0.7. Let's do a point at like 0.65. And we're now at 1.5 milliamps at 0.65 volts. Okay, we're now really coming up off the axis. And then at 0.7, you can see the current is really climbing now. We are now at 3.9 milliamps. Okay, at 0.7 volts, we're at 3.9 milliamps. And then if we try to go higher, we don't want to go above 10 milliamps because we're going to fry our diode. Well, it'll take more than that, but just for safety's sake. Okay, there's 0.75. We are now 8.7 milliamps. And if you're feeling really lucky, let's try to go to 0.8. I don't think we're going to make it. We're pushing our luck a little bit, but these diodes are actually good to about 100 milliamps. Oops. So there's 0.8 volts. We're at 17.2 milliamps. So that should be enough points to put together a nice curve of the diode in forward bias, just like we saw on the right-hand side. Okay, so we've got our forward bias curve. Okay, let's turn the voltage back down because now we have to touch our circuit. So we turn the voltage all the way down to 0. Now to do reverse bias, all we've got to do is take the diode out and flip it upside down. It's not hot, which is a good thing. So we're going to flip the diode upside down with the stripe now facing upward instead of downward. So now we're going to look at reverse bias. And what we're going to find in reverse bias is it's pretty boring. So here's 0 volts, 0 current, just like we had before. And as we start to crank this up, we're going up to 5 volts, still nothing. 10 volts, still no current. So we don't even need to take any points in between. If it's at 0 current with 0 volts and 0 current at 10 volts, it's going to be 0 current everywhere in between. And these diodes will actually withstand close to 200 volts before they start to let go. So here we are at 15 volts, still nothing. 20 volts, still we're only passing 2.1 microamps of current. It's basically nothing. So these diodes are very good in reverse bias. They really do not leak a whole lot. One thing that I'd like you to take note of is we always treated ISOBES, the reverse saturation current, as a constant, but you can actually see that it does vary a little bit with the applied voltage. Okay, so that completes our point for one curve. So let's do a different diode. So let's try the germanium diode. What I do when students are in here, they have to do one diode and then they can do others for extra credit. Some students are really macho. They'll do a third diode for extra credit. So we'll just do a second one. Okay, that's this diode here. So the diode is in with the stripe down, which means we're doing forward bias. So again, we're going to start at 0 and crank this up until we get to either 10 volts or 10 milliamps, whichever comes first. So there's at 0 voltage, we got 11.5 millivolts of voltage with basically 0 current. So let's bring this up to 100 millivolts. Oops, I went a little too far. It's very touchy. Oops, that's 300 millivolts. Let's try this again, having a brain fade here. Okay. There's about 100 millivolts, and again, we have a little bit more current leaking through, about 12 microamps at 0.1 volt. And then at 0.2 volts, we have around 150 microamps of current. This diode is really turning on much more rapidly. So at 0.3 volts, it's 1.7 milliamps. It's already starting to cut in, so this is most likely a germanium diode. Remember, they cut in around 0.3. There's 0.35 volts at about 5.08 milliamps, 5.09. And I don't even know if we're going to make it to 0.4. We may make it. Okay, something clicked. So there's 4, and we're at 13 milliamps at 0.4 volts of forward bias. So this one is really starting to conduct, and I don't think we're going to make it to 0.45. We're already up to 20 milliamps. We don't really want to go above that. So that's forward bias. We've only got about 4 or 5 points for that diode. So now we're going to turn the voltage all the way down, flip the diode upside down, and it's not hot to the touch, which is good. Plug it back in and do the same thing. So at 0 volts, we have 0.23 microamps of current. It's basically dead. So at 0.1 reverse bias, still 0.61, 0.6 microamps. 0.2, 0.3. There's still no current showing. Still no current showing. So we're at 3 volts of reverse bias already, and there's still no current. There's 5 volts of reverse bias. 6, 7, 8, 9, 10. So even at 10 volts of reverse bias, we've got 2.5 microamps of current, which again will not really show up on your graph. So that's the second diode. And then for those of you who are macho want to try the third diode, let's try this is the Zener, right? The black one?
No, that's the Schottky.
Okay, this is the
Bigger of
the little one?
Yeah, that one.
Okay. And just to demonstrate what the Zener diode would look like, let's just plug that in reverse bias. And we'll show you what the Zener diode does. So at 0 volts, there's nothing. And when you crank it up, there's 0.6, still no current, 0.7, 0.8, 0.9, 1 volt, no current. There's 2 volts, no current. 3 volts, it's starting to come alive. We've got about 30 microamps of current here. 4 volts, we now have half a milliamp flowing. And when we get to 4.5 volts, we're now at 2 milliamps. And by the time we get to 5 volts, I don't even know if we're going to make it. At 5 volts, okay, we now have 17 milliamps of current flowing. So this is a Zener diode. It's about a 5-volt Zener diode, and you can see when you get to 5 volts of reverse bias, the stripe is up. It's now flowing a substantial current. So, and we saw that on the curve tracer earlier. So that concludes what you've got to do for part 1. So for your lab report, you should be graphing your IV curves for each of these diodes, for at least for the first 2, and then put those in your lab report. And we are ready to move on. So we'll stop here, and then we'll pick up with part 2 of the experiment.